in the applications of ML/AI in biomedical analysis. Sir, we welcome you and request you to kindly address our audience.
Okay. Thank you very much for nice introduction. And I would like to thank this Synaptics Club IIT Indore and Aryan Rastogi for providing me this opportunity to deliver a talk in this lecture series. Thank you very much for this opportunity. And in this talk, we will see this machine learning techniques, how they are useful for development of automated systems that can be used to identify the signals which are normal class and abnormal class. For example, a person has epileptic seizures and the person is normal, and how to identify it automatically. So machine learning algorithms can help and to design automated system, intelligent system, expert systems. And here actually we will also see use of signal processing techniques, like signal analysis techniques. They can decompose the signal into simple components, simple modes, where nicely you can extract features, and the features can be used for the automated classification of signals. And in this talk, actually, we will see the advanced signal processing techniques, for example, empirical mode decomposition and time frequency analysis based on the pseudo Wigner-Wille distribution and multivariate transform. And before this, these together with I will also try to give you basics related to these signal processing techniques and also background, so that it will be easy to understand for you. And this actually signal processing technique is one of the important part. And these days, actually, what is happening most of the most of the places and most of the research, you will find that the signal processing part is missing. So signal processing actually can help you to provide a nice set of features, and this nice set of features can be associated with the disease label. So this analysis not is just only for useful for classification purpose, but it is very useful for the interpretation of the disease, interpretation of the signal level or disease level. That is also one of the important parts. So if you are just simply interested in the classification part, then machine learning can help you. But together with the classification part, if you are interested in interpretation, analysis, then actually signal processing part is also important. So in this talk, the signal processing and machine learning techniques will be emphasized, and you see how we can develop very nice systems that actually can be used for the automated detection of the abnormality that is actually detected using various medical signals. So with this background, let us start. So let me share my slides. Are you able to see the slides?
Yes, sir.
Okay. So the title of this talk is Introduction to Artificial Intelligence Machine Learning Techniques and its applications for brain signal classification. And these days, actually, this AI ML, this is very common term. Even if you see, like even school kids, they are also talking about the machine learning, artificial intelligence. This is actually one of the requirement of time. And everybody these days, everybody is interested in the automation. They want to develop intelligent systems, expert systems, automated systems, and where this machine learning actually plays important role. So this is actually overview of this talk. First, we will see introduction of machine learning, and after that, we will see various applications of machine learning for Eeg signal analysis. And then this developed methods. Recently, actually, our group has developed some methods which are based on signal processing machine learning techniques for analysis of normal and seizure Eeg signals, classification of seizure and non-seizure Eeg signals, and detection of epileptic seizures. And after that, is time frequency image based features for classification of sleep stages, that also will be explained. And then you will see multivariate decomposition based features for human emotion classification. And in the end, conclusion will be provided. So all these techniques actually, like for example, if you want to identify human emotion, and then the signals like biomedical signals, electroencephalogram signals, they are very useful, and they are found to be more reliable and nicely actually, like most of the techniques for this classification of emotions, that is based on the face recognition, based on the speech identification. But these kind of modalities, these kind of methods for identification of emotion can be misleading. They are not reliable. And then you will see in this talk, these EEG signals, medical signals, how they are able to identify the human emotions. So with this, we will see in this coming talk in this details. So machine learning, that is actually one of the very common term. And we actually in our life, if you see, we always learn, because like for example, newborn baby, and for him or her, mother is the first teacher, and mother teaches the baby that she introduces to the newborn baby to entire world. She say, this is your uncle, family members, relatives. And after some time, actually this baby, he or she learn, and after learning, he or she doesn't ask to mother, who is uncle, who is auntie, who is mother, who is grandmother. Everything actually has been learned by the baby. And that is same actually, then after that he did himself. Whatever he does according to, based on the training, he always perform the testing. The same concept what we actually learn in our real life, that same thing we want to do with the machines or computers. So that actually, that is the term, this machine learning. Machine learning, this means whatever learning process that we have, same kind of mechanism that we want to have with the computers, with the machines. And this machine learning is actually one umbrella term. It is a set of techniques, collection of methods and tools which can help computers to learn and adapt on their own. So there are various learning methods based on that. Actually, according to your problem, we have different kind of learning, and that is inspired from the nature. And according to Herbert Simon, the learning is any process by which system improves performance from experience. So based on the experience, actually we learn. And similarly, during the machine learning, based on the like sometimes when you are using internet, and when you are surfing, and then you will find that based on your searching, and similar kind of advertisement comes. So that actually, that feedback or experience, that machine learning techniques, they understand, they try to understand your choice, try to understand your what kind of interest you have, what kind of hobbies you have, based on your searching, and accordingly you will see the display of the objective display of the actually things in which you are interested. For example, if you buy good shoes from this internet, from this by using this, and they will the internet, this based on machine learning, they will understand. And next time whenever you will join, or when you search, then good shoes will be displayed, so that because they will understand your requirement. So that actually this machine learning techniques, they're very useful for the recommendations whenever you are watching some video, and according to that they will understand. Like if you see the spiritual video, then different spiritual video will come in the line, in the queue. So this machine learning, they can understand based on your actions, based on your surfing, based on your search, in which kind of data, which kind of information you are interested. So this machine learning techniques actually has got various applications. These applications include automated health diagnostic systems. So like whenever you go to hospital, doctors actually they take your data. They, for example, electroencephalogram, EEG signal, electrocardiogram signal, and different signal. Then they print on paper, and they perform the scanning, visual scanning. So this actually cannot, and now with the help of machine learning, we have such nice system that automatically you can have decision. So decision making systems can be developed, intelligent systems can be developed, expert systems can be developed for automated health diagnosis system. and product recommendations automatically based on your activities on the internet. The products will be recommended, and image recognition. You can see based on your face, based on that something can be controlled. Like based on your face, you can control your mobile. You can control. You can open the door based on the face recognition. So if you belong to that room, then automatically that face will be recognized and door will automatically open. So these all actually sentiment analysis, fraud detection in banking domain, language translation, and like sometimes for security purpose, we have actually the border, we record the signals in other language, and that actually machine learning techniques, we teach them, we train them to the translation. Whatever is received, whatever audio is received, that will be converted into different language. So that language translation can be done, and also automated language translation. It has medical diagnosis, stock market trading, virtual personal assistant, email spam and malware filtering, self-driving cars. These days, driverless cars are coming, and automatically actually based on the driving, they take the feedback, reinforcement learning, like so whatever according to you don't know, and according to situation you have to take decision, and that actually driverless car where this machine learning plays important role, and this machine has to take decision like a human based on the obstacle, based on the type of road we drive the car, and similarly that car has to be driven by the machine, by the computers, by using this machine learning method. So it has actually traffic prediction based on the, these days you will find automated traffic prediction based on the density of the people. That's signaling is controlled. So there is image recognition. So various actually it is very difficult to find any area of science and technology these days where you will not find use of machine learning. Machine learning has been entered completely in all areas, and this machine learning, when you see in broad manner, then it has two important parts. So like training and testing data. So for example, so you have joined this IIT Indore in your BTech program. So you study this for 4 years, and in 4 years you get very good training, and you have learned various concepts of your engineering branch or whatever branch you have taken admission. And after that, these 4 years, based on your training, now you are efficient and you have trained, and now now you can actually you can go to some companies, you can got that expertise, and that can be tested. So the similar kind of, we have training and testing. So this, during this training we learn, and once it is learned, then we perform the testing, and that is actually the same part. Similarly, like in defense, if you join the defense, they will provide you training, and once you are trained, then they find you fit for the defense service, and then you will do proper your duties. So similar way, this machine learning techniques also, there are two important parts. One is training, and second one is testing. So the training actually, that is based on the features. So like whenever you see a person, and quickly you identify that person based on the features. So these features may be size of eyes, size of nose, size of ears, and different kind of features that we see, and we quickly identify the person. Similarly, that we do for the data also. So the observations in the training set from the experience, which the algorithm you use to learn, that is actually that is the training. For learning whatever features we use, that is known as training data. And the test set is the set of observations that is used to evaluate the performance of the model based on the performance metric. So that is actually used for the testing purpose. So whatever features set we have, some features we use for training purpose, and some features we use for the testing purpose. And there are actually, based on the data, now there are mainly three important machine learning algorithms. One is supervised, unsupervised, and reinforcement learning. Supervised learning means you know the target, you know the, like whatever the classification you have to do, so you know what is the actual outcome that is known to you. And so unsupervised learning, you don't know the target, and you don't know what is the correct value for the particular problem, what is the correct outcome. So that is actually unknown. So that this kind of learning actually learns from the data itself. And reinforcement learning, that is actually based on the feedback. So based on the feedback, actually it learns how to train the data. So the training is based on the feedback, trial and error, and it starts learning, then whatever I learn based on that experience, and then again it learns. So that is similar to we do in life. And there are various types of classifiers, and you can see in this figure, this X and Y, these are the features, two set of features. So one is X and Y, and it has different values for class A, class B. And here, this simple line that is actually boundary, this can classify these two classes. And that is actually the purpose of this classifiers. Okay, classifiers classifies data into two classes. So it can automatically classify. But even these days, you will see the given classes people are using machine learning in that when they are conducting tutorial class, and by using this machine learning algorithm based on the brain signals, they can determine who is serious in the class and who is not serious in the class, or who is learning whatever is taught and who is not learning whatever is taught. So that actually this kind of different classes, if you have in real life, and they can be actually nicely separated using this classification. And so, for example, if when you cross the road, then you see both sides, and the car is coming, and then you see what is the distance of the car and what is the speed of the car. So these are the features. Based on that features, you take the decision. So similarly, for the signals, for the real life, whatever objects you want to classify, that is based on the features. And features actually very important part. And there are various types of classifiers, that is k-nearest neighbors, KNN, artificial neural network, support vector machine, naive-Bayes, decision tree, logistic regression. And these days, actually, there is a lot of interest in the smart healthcare monitoring system for the machine learning methods. So you see, this actually world is full with signals, but this is also true with our body. Human body is full with the signals, and you can even record many signals from the human body. And human body, you can see this electroencephalogram, Eeg signal, blood pressure, blood sugar, oxygen saturation, heart rate, position, activity, electromyogram, respiratory rate, cholesterol level, electrocardiogram. So these so many signals actually can be recorded from actually by using this smart healthcare monitoring system. And these days, actually, what is happening? People are believing that we go to based on the machine learning algorithms, like what generally we approach the hospital, and based on this automated systems, based on this automated diagnosis system, and once this abnormality takes place and these physiological signals, these features will be extracted and they will be transmitted to the hospital. And these hospitals, doctors and the clinical staff will know about your abnormality, and based on this your location, global positioning system, GPS, and they can actually reach to you. So that is actually even doctors can come to you whenever you are not well. So that is actually one of the important aspect of smart healthcare monitoring system. So it can monitor you always. So these signals actually we determine this based on the different sensors. These signals are recorded, and then we have big data. That is big data, and we also have this electronic medical records. And based on that, this entire data, we can actually have feature and pre-processing. We have deep learning, machine learning techniques, and then actually we can detect whether you have heart disease or not, absence or presence, and then on that basis, it will be informed to the patient, it will be informed to the hospital, data manager, everybody will know. Even your relatives, your family members, they are staying in other countries, they will also know what is actually happening to you. So this machine learning technique is one of the very important part actually for healthcare system. And that is actually in Hindi, there is one saying, पहला सुख है निरोगी काया, दूसरा सुख है हाथ में माया. So this means actually health is better than wealth. Even if you are a rich person, it doesn't matter. If you are healthy, then you are the richest person in the world. So person is poor. It is not problem, but a person should be rich from the health point of view. And that is actually in English saying health is wealth. But according to saying in Hindi, health is better than wealth. So health is actually very important part, and where this machine learning algorithms play important role. And you can develop automated systems, intelligent systems, expert system, monitoring systems, and even these days actually many diseases they can be monitored through this machine learning algorithms. And quickly, whenever the alarm will be on, like whenever you have some abnormality, and then alarm will be on and your family members will know that. So we will see very interesting applications in the stock for brain related diseases. And this, so actually in this talk our focus will be more on Eeg signal processing using machine learning technique. And human brain is very complicated and it is highly non-linear system. And whatever actually, even if you see these Eeg signals that we record from the brain, they are highly subjective in nature. So like even the different trials we record, for example, 4 or 5 times Eeg signal from a person, different trials. Even during these trials, our signals are not same. They are highly variable. So this electroencephalogram that we call Eeg signal, which measures the electrical activity of the brain, which is generated by the neurons. And Eeg signal is actually one of the important signature, one of the important tool which doctors generally use to diagnose the various brain related disorders. And if you have any brain related abnormality, and if you go to hospital and doctors, they will take your Eeg signal, and based on that they will interpret your disease, they will detect what kind of disorder you have. So Eeg signal is a very useful tool for in order to investigate different physiological and pathological issues of the human brain. And the quantitative analysis of Eeg signal is a challenging task because these Eeg signals they are very complex, and sometimes these signals have actually irregular nature. And like even if you limit the signal for a small scale, then also the signal actually nature is not clear, and it is non-stationary signal. So in signal processing, we use mathematical models to represent the signal, and if any of the parameter of these models change with time, then such signals are known as non-stationary signal. And Eeg signal falls in actually in such kind of category, where even you limit Eeg signal for very small amount of length or a small less number of samples, then also this actually Eeg signal is non-stationary signal. So due to that, it is very difficult to develop quantitative method, like one kind of algorithm, that kind of mathematical technique to show the difference between the signals. So due to that, actually, there is a lot of interest in the literature to work in this direction. And generally, what actually happens when you have brain-related disease, and if you go to a doctor and the hospital, and then they will record your Eeg signal, and then they print on the paper and they perform visual scanning of that. So that visual scanning based diagnosis method for brain disorders, that is very time consuming, and also sometimes actually doctors are less and some patients are many. So it is actually it is difficult to monitor your signal based on the visual manner. For example, like you are admitted in hospital, and this 2 hours, and it is difficult for doctor to be there for 2 hours to see your signal how it is changing. So it is also inaccurate also, maybe because when you print it on the paper, then sometimes this variation or signal, large amount of signal, that actually that will not be visible. That actually when you print on the paper, so when you go for large amount of data, then variations in the signal will not be clear due to use of large scale, and it may be very complicated also. So like if it is difficult, suppose somebody is admitted in hospital for 1 day, 2 day, and it is subject to judgment and suffers from human error. You must have heard that in hospitals, like people talk, this doctor is saying this is the disease, and let us have opinion of other neurologists. So this actually, whatever methods we have, they are not complete. They are not actually, this may be suffer from human error. So also this kind of diagnosis method, it is generally performed by the trained professionals. They have training, they have experience, expertise, and the disease doesn't see whether you are actually educated or you are illiterate, or you are IS officer, or you are professor, or you are a student, or you are a rich person or poor person. For disease, everyone is same. So that actually this method, whatever we want to develop, that should be such method which can be used by the common people. So that is actually one of the motivation of such kind of research. And so due to these reasons, there is a lot of interest in the literature to develop features like this, what features are useful to machine learning techniques, and what features are useful, what are the feature reduction techniques, because most whatever features you are selecting, what you are obtaining, they all are not useful, and you have to apply feature reduction techniques so that meaningful features can be useful to represent the class of signals. And based on the machine learning techniques, these features can be connected together with classification system. So this actually in the literature, it has a lot of interest to develop. It has many applications also. So this kind of actually systems, intelligent systems, expert systems that we design in biomedical, that has actually three important parts. One is signal analysis, and second one is features, and third one is classifier. So these three actually you will see in this talk how these three components are able to provide you the automated identification system for the diagnosis of a disease. So first actually part in this talk, it is based on the analysis, classification, detection of epileptic seizures. So epileptic seizure, this is also known as epilepsy. In Hindi, we call it mirgi, and it's the result of transient and unexpected electrical disturbance of the brain. So like in brain, these all neurons, they synchronize together and they generate very high electrical activity. So due to that, this actually due to higher this electricity or electricity current in the brain, this brain activity disturbs, and brain is the master of the body. Once brain is disturbed, then all actually parts of the body, they are connected with the brain, and this entire body is disturbed. So it is very serious disease, and it affects around 2% population of the world. And we have proposed this area parameter for analysis of normal and epileptic seizure Eeg signals, and bandwidth parameters for classification of seizure and non-seizure Eeg signals, and the instantaneous area for the automated detection of epileptic seizures. So this normal means these people, they never had epilepsy disease, and epileptic seizure means they have seizure disease, and non-seizure means it includes seizure free and normal class. Seizure free means earlier they were patient of epilepsy and now treatment has been done and now they are seizure free. And all these methods actually will be explained in the detail. And these are the proposed methods. They are based on the empirical mode decomposition based features. So before starting this empirical mode decomposition, just briefly, I will actually explain you the signal processing part, that in a simple manner. So the first actually the signal analysis, whenever you have signal, it has information. So this information we use actually signal representation transform to obtain that information. And signal processing, one of the transform is Fourier transform. So in Fourier transform, we represent signal in terms of sinusoidal functions, and these sinusoidal functions they have actually infinite spread, they are periodic functions. So due to this infinite spread, the resolution, concentration or localization of these basis functions, that is zero. So resolution or localization, that is proportional to 1 upon spread, and this spread is infinite for such basis functions. So due to that, this resolution is zero. And non-stationary signals that you have seen, their parameters, they change with time. So in order to represent such kind of actually signals, this Fourier transform based method is not suitable because these basis functions are not suitable for non-stationary signals. So motivated by that, short time Fourier transform, which we call STFT, that was actually proposed. So in a short time Fourier transform, actually what we do, we actually whatever signal we have, we divide the signal into different segments, and each segment we assume that signal is stationary, and then we apply Fourier transform to a segment, and arrangement of these Fourier transform of different segments gives you short time Fourier transform. And in that way, we can analyze non-stationary signal. But this kind of method again has some problem, there is no thumb rule which will suggest what should be the size of the window function that we use in STFT to isolate the signal, and what is the type of the window and what is the size of the window. So when you have low frequency component, then we want to have large size of the window, and when you have high frequency component, then we want to have narrow analysis window. So that flexibility was not available in the short time Fourier transform. Then actually for that, wavelet transform was proposed, and that we actually use scale function. So that we look signal at different penny scales. So when you see signal at low scale, it gives you good time resolution that is suitable for high frequency components present in the signal. And when you see signal at large scale, then it is suitable for low frequency component, which gives you good frequency resolution. So in that way, we can have multi-resolution analysis for the signal analysis. And this wavelet transform also, there is no actually, this can be implemented with the help of filter bank. And there is no rule which will suggest us what should be the number of labels for this wavelet decomposition and what should be the mother wavelet. So that is actually motivated by, that was the problem, and based on these actually motivations, and this was actually this empirical mode decomposition was proposed in 1998 by Wang and others. And this empirical mode decomposition method that actually doesn't use any basis function. So in case of Fourier transform, short time Fourier transform, wavelet transform, we were representing signal in terms of non-basis functions. And here these basis functions actually we designed from our side. But EMD method, empirical mode decomposition based method, we don't design basis function from our side. We actually try to get such basis function from the signal itself. So that actually this empirical mode decomposition, this method has come up with the computer science actually people, they proposed by the computer science scientists. So they, instead of using this mathematical formula, they come up with one algorithm, and that algorithm actually can decompose signal. So where you don't need mathematical formula, just one shifting algorithm is required, and that algorithm can actually give you the components or basis functions. And it makes sense also, like physiological interpretation can be done, because these biomedical signals, electroencephalogram, Eeg signals, they are not actually, we don't know what kind of natures they have, and forcefully we represent them in terms of basis functions. And if you extract basis functions from the signal itself, then you have a nice interpretation, and like the basis function itself will be the part of the signal. So with this background, now we can understand this EMD. So this Eeg signal that has been recorded from the person, then we apply this intrinsic mode functions IMFs, then we obtain IMFs using EMD method, and then we apply analytic signal representation that is obtained using Hilbert transform of the IMFs, and then area feature which is based on the modified center tendency measure that has been used, and then we apply Kruskal-Weiss statistical test, which gives you statistically significant difference between normal and seizure Eeg signals. And the other method, this analytic signal representation of IMFs or analytic IMFs, then actually we determine this amplitude modulation and frequency modulation bandwidth features. So that we will see, then these features have been used as an input to least square support vector machine classifier, and that will give you seizure and non-seizure Eeg signals. And third method, we have proposed instantaneous area feature, and that together with DCR rules provide actually nice epileptic seizure detection. So that these three methods will be explained actually in detailed manner in the coming slides. So for this study purpose, we have taken this Eeg data set, which is publicly available by the University of Bonn, Germany. And this database, this is actually available for the research purpose. So this database has been recorded by the neurologist, and based on the visual inspection of the signals, they have actually identified, they have segregated this data into different classes. So it has recording from the normal persons, it has recording from the abnormal person, it has recording from the seizure free. Earlier they were patient, now they are treated. So in that way, this data set has actually three classes majorly. One is normal class, second one is seizure class, and third one is seizure free. And when you combine seizure free and normal, then we call it non-seizure. So this subset Z, O, N, F, S, these are 5 subsets, and each subset has 100 EEG signals, and the subset Z includes the 100 EEG signal recorded from the eyes open healthy subjects, and the subset O includes 100 EEG signal recorded from the eyes closed condition from the healthy subjects, and subsets N and F, they include 100, 200 EEG signal recorded from the seizure-free subjects, and S, actually subset S, includes 100 EEG signals recorded from the seizure subjects. So each subset includes 100 EEG signals, and duration of each EEG signal is 23.6 seconds. And sampling frequency of EEG signals in the data set is 173.61 Hz. And these signals actually have been recorded with 128 channel amplifier system using common difference. And EMD method that already actually you have seen, which is suitable for analysis of nonlinear non-stationary signals. And this is an adaptive method. It does not require any condition about the stationarity or linearity of the data. Whatever data you give to this method, it will decompose it, and nicely actually you can have components, you can have modes, and these modes are actually modes are nicely well-behaved modes, and they have a specific property that actually can be used. So these questions actually, after this talk, we will take these questions one by one, and I will be happy to answer them. So this data-dependent method, you don't need to design any basis functions from your side, and just it's actually this is just you give any data, any signal, it will decompose automatically. So this is automated method, data-dependent method, and it can decompose a signal in terms of narrowband intrinsic mode functions. So these IMFs, whatever we obtain, we can consider them narrowband, and due to this nature, this can be modeled using amplitude and frequency modulated signal, AMFM signal model. That is actually very important. So what actually this AMF model, that is more general model of the sinusoidal model, like that we use in Fourier transform. So these sinusoidal functions, their amplitude and frequency, they are constant with respect to time. But in this case, we can consider them to be allowed. The time and frequency, this amplitude and frequency, they are allowing, they are changing with time. So that actually that results AMFM kind of model, amplitude and frequency modulated sinusoidal model. So that actually this method, EMD method, gives you nice AMFM components, and which are narrowband in nature. And this each IMF satisfies two basic conditions. Number of extrema and the number of zero crossings must be the same or differ at most by 1. This is the first condition. This condition ensures that whatever IMF you have obtained using EMD method, that is some like sine cosine function. And the second condition, the mean value of the envelopes, which is defined by the local maxima and local minima 0. So this condition ensures that whatever IMFs you obtain, that is symmetric in nature. So these two conditions are very important, and based on these conditions, these basis functions actually, what we do, we have data, then we determine the maxima, minima, then we interpolate maxima, interpolate minima, then we have two envelopes, and we take the average of these two envelopes. So this whatever we get the average envelope, then we subtract from the signal, and then we check these two conditions from that residual, and if these conditions are satisfied, then we say it is IMF. Otherwise, we repeat this process again and again. So in that way, we actually determine all possible IMFs from the signal based on these residuals. So in the end, the signal, like in equation 1, you can see signal can be represented with the help of IMFs plus residual. So this residual is the time-varying DC component. It is monotonic component from which no further IMFs can be derived. So this is very, actually these IMFs, one example we can see, this is like Eeg signal, and this is have when signal actually, this EEG signal when you record during epilepsy. So this is epileptic seizure EEG signal, and it has got very two interesting features that generally doctors actually do when actually uh, this. I will take these questions later actually this after this completing this talk. So these seizures, they actually it has got spikes because all neurons they synchronize together, and due to these spikes, that actually this is one of the feature, and that doctors they recognize it by visual inspection. And second feature, it has large amplitude. So when you decompose this actually in some of the signal processing techniques, when you perform analysis, then you want to have such kind of features that is actually based on your based on by machines by your that machine learning. So based on these features, we identify that pattern, and same thing we want to do this by the machine. That is actually machine learning. And there is one question, nice question: what is the difference between artificial intelligence and machine learning? Artificial intelligence, that is actually we have intelligence, and we want to have such kind of intelligence with the system, with the methods, or with the computer, with the machines. That intelligence means the capability of thinking. That is the thinking. Like when you are a very small child, he doesn't have decision making capability like a 1 year old or very small child. But when you learn, then you can make the decisions, and you know what is right, what is wrong, what is false, what is truth, and that babies don't know. So that decision making, that intelligence, once you develop, that same kind of phenomena, same kind of same kind of structure, if you can develop in any device, any machine, any or computer, that is artificial intelligence. And what the process you are doing, that process is that actually that is machine learning. Yes. So what the process that you use to make the decision, that is the process by like you are extracting features. So here this doctors, when you go to hospital, doctors will see your EEG signal, he will see the spikes, he will see the large amplitude of the signal, and based on that he will take decision. So this is actually this human decision system. Now if you are able to have such kind of system with the help of machine learning, then that is actually use of the machine learning. So decision making, the process, that is actually the part of machine learning, and the decisions making capability of that is the part of artificial intelligence. So artificial intelligence means you can have such kind of, now this machine computer is able to identify the seizures using this EEG signal, then that computer actually has artificial intelligence because that has capability to that. But how it is done, that is part of machine learning algorithm. I think it is clear. Is it clear? Yeah. Okay. So here you can see now this epileptic seizure EEG signal, we actually can be decomposed nicely, a set of components using this EMD method, and they are well symmetric components. And now after that, these components can be actually converted into nice set of features. So what we have done, this narrowband signals or narrowband IMF that we have obtained using EMD method, then we have applied Hilbert transform to this signal. So this Hilbert transform, for example, the CT is the signal or IMF plus J times its Hilbert transform, that gives you analytic IMF, so complex intrinsic mode function. So here this AT is the time varying amplitude and phi t is the time varying phase, and its derivative gives you the instantaneous frequency. So in that way, for the each IMF, we can determine the analytic signal representation. So for the nth IMF, analytic signal representation is given by the equation 2. And this analytic signal representation has got very two interesting properties. When you plot it, then it has direction of rotation, and the rotation in the plot has unique center. So we see as very nice structure actually. So this Eeg signal without any decomposition, if you obtain analytic signal representation, then you see there is no geometrical structure. You don't. There are multiple centers, and there is difficult to find out a specific geometry. On the other hand, if you see the analytic signal representation of IMFs, IMF1, IMF2, IMF3, IMF4, and here you can see nice circular symmetry is there. So this we can determine area parameter from this actually circular patterns. That area parameter is so simple parameter that anybody can understand. Even if you explain this to farmers, they can also interpret the area. Even if he is literate or illiterate, it doesn't matter. The area is such simple parameter, and it is anybody can understand. And what actually this area parameter we have linked it with the epileptic seizure. So whenever person has seizure, then area parameter become large, and when person is normal, area parameter will be less. So this kind of actually observation, this kind of process can be implemented in the form of software, and based on that boundary, based on the threshold, one can actually design the alarming system. So whenever the pulse area is becoming larger by some specified value, then alarm will be on, and that person will be given warning that he is going to have epilepsy attack. So now how to compute this area in automated manner? So then we have actually proposed modify center tendency measure, and which can determine this radius required for the area, and from the radius we can determine the area parameter. So for that, this method we have proposed this equation 3 as a modified center tendency measure. And if suppose you have to n total number of points and r is the radius of the central area, then modified CTM is given by the equation 3. So here, what we do actually, we select the radius, and for this radius we determine the CTM, number of points which are falling for the given radius out of the total number of points. So here you can 95% CTM. So out of total number of 95% points are inside the radius. That according to the CTM, actually we determine the radius, and according to the radius we determine the area. So here E equals to by a simple formula based on that area can be computed, and then this area we have actually converted into instantaneous area. So like so that you can determine presence of epileptic seizure at any point of time. So that is also one of the important requirement for instantaneous detection of epileptic seizures. So for that we have actually we have IMF, and then we have segmented it into different times, and then for each time, each segment, we have determined the area parameter. So in that we have interpolated all area values, and then nice we have instantaneous area. So this is actually computed using moving window method, and the window size for this performing this computing instantaneous area, that is like 3,840 samples. So, and this window size is uniform for all Eeg signals. So that is actually a mathematical representation of this instantaneous area of mth IMF can be defined by the equation 4. And this another actually concept that we have used for the classification of the seizure and non-seizure Eeg signals, that is AM/FM bandwidth. So in signal processing or signal system, whenever you have done that course, you will see whenever we talk about the bandwidth of any signal or system, then actually we see the spread of the signal in frequency domain. So Fourier transform, and that spread in the frequency domain, and based on that actually we say that this is the bandwidth of the signal. But at 1990, this Cohen and Lee, they come up with a different kind of definition for the bandwidth. This bandwidth or spread in the frequency domain that depends on the time varying amplitude and time varying frequency. So by changing amplitude and frequency, actually we can control the bandwidth of the signal. So that now how to determine that, actually how to get such kind of AM/FM component in order to have such kind of bandwidth. So the equation 5, based on that interpretation, you can have two components of the bandwidth due to amplitude modulation and bandwidth due to frequency modulation. And how to determine these two bands, these are the mathematical expression that you can see in equation 5. And now real life signals, whatever you see, they all are actually they are broad. They are they have multiple frequencies. They are broadband, and they are not narrowband. So for that, in order to have this EMD method, gives you a platform where nicely you can represent this multi-band signal or this multi-component signal in terms of monocomponent AM/FM signal. So this each IMM can be represented by the AM/FM signal, and we can determine these bandwidth for each IMM, and these bandwidth they can be used as their features for the classification of seizure and non-seizure EEG signals. So after this, now these three methods, now we will see some results. And first part actually in this results, that is analysis of normal and seizure EEG signals. So the subset Z from the normal class and subset S from the seizure class. And this method can detect patient with epilepsy using EEG signals from the normal people. And EMD method makes possible to cover more than 95% of data points which lie within the circle due to having a circular form of the analytic IMFs. And area parameters actually have been estimated for both the classes, normal and seizure, based on the analytic signal representation of IMFs of various window lengths, that is 500 samples, 1000 samples, 2000 samples, and 4000 samples that we will see. So here you can see the CTM in terms of percentage is plotted as a function of radius, and for normal class, if you, in order to have very high CTM, for example 100% CTM, that is maximum, you require radius around 300. On the other hand, for seizure case, requirement of radius is actually 1200. So this seizure case actually it has more variability as compared to the normal case. So that actually that feature has been incorporated for the nice analysis of the seizure and normal classes of EEG signals. So once the radius is larger, this as a result, corresponding area will be also larger. So in seizure case, area is larger, and normal case it is lesser. And then we have actually used this Kruskal-Weiss statistical test, and which actually for window size of 4000 samples, and based on this statistical test, it gives you this box plot and probability value. And the probability value, if it is coming less than 0.05 or 5%, and then we call statistically significant difference between two classes. So here you can see in all cases, these first four IMFs that we obtained from the EEG signal, their box plots, they are showing statistically significant difference for this window length of 4000 samples. Then same thing actually true for window length of 2048 samples. And here in this case also, this first IMF, second IMF, third IMF, fourth IMF, they are showing the probability value coming out to be 0. That is less than 0.5, 0.05 or 5%. And the same thing actually we can see in the case of window length of 2000 samples. And here also this area parameter for normal epileptic seizure intervals, they are well separated, and that probability for that is actually also 0. And the same thing that is actually for 1000 samples also. And here you can see this area parameter is able to discriminate these two classes in nice manner. And this in same thing is true for 500 samples. In this case also, it's all four IMFs. They actually they have probability value equals to 0. This means they have statistically significant difference between two classes. And this actually, whatever we have seen from the box plots, same thing here we can see in terms of quantitative values. So the subject normal and seizure window size is 500, 1000, 2000, 4000 samples. And IMF1, IMF2, IMF3, IMF4, this minimum, maximum, median value of the area parameter is shown. And from this table, it is clear that this area parameter is nicely separated for the normal class and seizure classes. And there is a lot of actually work in the literature. People use machine learning methods and signal processing techniques like Decom and others done for. They use nonlinear pre-processing filter, diagnostic artificial neural network, and they got 97.2% classification accuracy. Srinivasan and others 2005, they use time and frequency domain features and recurrent neural network, and they got 99.6% classification accuracy. And Kanathan and others 2005, they use entropy measures, adaptive neurophagy interface inference system, and they got 92.22% classification accuracy. And Polat and others, they use fast Fourier transform and decision tree, they got 98.22% classification accuracy. Suvasi in 2007, he applied discrete wavelet transform, and mixture of expert model got 95% classification accuracy. And our proposed method, this actually is based on the area parameter of the analytic IMFs, which gives you 100% accuracy because it doesn't require machine learning technique. next method, we will see why we need machine learning techniques. So here actually our analysis part itself is a strong part. Selection of the spoon depends on the type of food. Suppose if you want to have noodles, then you use fork because your food is discontinuous and your spoon is also discontinuous. So discontinuous food can be nicely handled with the help of discontinuous spoon, that is noodles, that is fork. So similarly, luckily, we have got such signal analysis technique, which is actually highly suitable for the class of Eeg signal that actually we are analyzing. So there is no need of classification. Based on the simple threshold, we can separate these two classes. And after that, we have actually proposed the classification system for seizure and non-seizure Eeg signals. And here we need machine learning approaches to classify them. So in this actually subset Z, O, N, and F, they are combined to form non-seizure class, and the subset S from the seizure class. And in that, by doing such kind of actually framework, one can detect patients which have epilepsy from the normal and seizure-free people. And EMD method nicely decomposes non-linear and non-linear signals into a set of AM/FM components. And then we can determine nicely AM/FM bandwidths using this formula that has been shown in the previous slide. And these bandwidth features actually help us to find the contribution due to amplitude modulation and frequency modulation components. And these features, bandwidth features, can be used as a set of features to classify the seizure and non-seizure Eeg signals. And here you can see this is the bandwidth due to modulation of the IMF for seizure and non-seizure classes of Eeg signals. And the first four IMF, the seizure and non-seizure, here you can see bandwidth due to AM, and that is actually that shows the difference. And the remaining IMFs, 5 to 8 IMF, there is no difference between these two classes, seizure and non-seizure, using this bandwidth due to AM part, amplitude modulation part. Same thing we will see this bandwidth due to frequency modulation. So first four IMF, it is able to show the difference, but in remaining case it is not showing the difference. So now here you can see earlier case, this bandwidth, whatever area parameter, it was showing clear-cut difference, and based on the simple threshold, we can classify these two classes. But here in this domain, when you are going in such individual features, then you are not able to separate these two classes. So this is actually one of the important motivation for machine learning based technique and support vector machine, which actually projects the features into high dimensional space, where nicely you can separate out them. So that is actually this is a motivation for using support vector machine, and least square support vector machine is one of the actually improved version of the support vector machine. So here we now should we use all IMFs or not, so that actually that can be checked with the probability value of these features based on the Classifiers test. If probability value is coming out to be less than 0.05 or 5%, then those IMFs can be used or can be considered statistically significant IMF. So features corresponding to these IMFs, that will be a statistically significant feature, and based on that, we like first four IMFs, is bandwidth due to AM, bandwidth due to FM, they are statistically significant features because their probability values that is less than 5%, that is or 0.05. So now another remaining IMFs 5, 6, 7, 8, they are having probability value greater than 0.05. So they are not statistically significant. So due to these reasons, we have included this first four IMFs bandwidth features for the further classification using machine learning technique. So this actually this is the simple overview of the machine learning based on the support vector machine. Two-class support vector machine, we consider the following decision function, that is fx equal to sine wt gx plus b, and here w is the L dimensional weight vector, and gx is the mapping function, and b is the bias. So that is actually we use kernel functions for that we will see in the coming slides. And based on the sign parameters, based on sign, if sign is coming plus, then we take decision in favor of one class, and if sign is coming minus, then we take the decision in favor of another class. So in that way, binary classification or two classes can be classified using this two-class support vector machine. And this is a actually simple block diagram of this least square support vector machine based classifier. So features whatever we have obtained, for example AM, FM bandwidth features, then we use some set of features out of them, and then we use them as training set, and the remaining features will be used for testing purpose. So the first set of features, and there are various methods for this. Sometimes we use cross validation method also, like 10-fold cross validation. So what we do, we divide this feature into 10 parts, and we take 9 parts for the training and remaining part for testing, and we repeat this 10 times to different parts. Then average of all accuracy, that gives you the 10-fold cross validation accuracy. So this is also one kind of actually approach, and sometimes people use 5-fold, 2-fold also. So here in that we get some set of features for the training purpose, and together with this kernel functions and its parameters, we train this classifier. So once this classifier is trained, then the remaining set of features we use for the testing purpose. And these features, when you apply here, based on the trained system, based on sign, if it is plus, then it is one class, and if the sign is coming -1, then it's another class. So in that way, we can nicely classify two classes based on the sign of the decision function. So for this actually work, we have used following kernel functions: polynomial kernel, that is shown by the equation 7, and where L is the degree of polynomial, and radial basis function, that is actually represented by the equation 8, where sigma controls the width of the RBF kernel. So here there is no thumb rule which will suggest you what should be the kernel or polynomial kernel, what should be the radial basis function, what is the order, what is the sigma. So these all are actually based on trial and error method, and it depends on the data which you are classifying, and accordingly that you can select different parameters of these kernel functions. Mexican head wavelet kernel function, that is also actually used, which is shown mathematically by equation 9, and Mollet wavelet kernel function, which is defined by the equation 10. So these actually kernel functions have been used in this work, and this once you have this classification system, then you want to know how is the classification process, what is how to measure the effectiveness of the classifier. So that actually there are some certain measures, and we have used some performance measures to see the performance of the proposed classification system, so which includes sensitivity, specificity, and accuracy. So sensitivity is the proportion of the epileptic seizures which are correctly detected by the algorithm, and mathematically it is represented by sensitivity in terms of percentage, that is TP upon TP plus FN. So TP means true positive and FN means false negative, and specificity is the proportion of the segments without seizures which is correctly identified by the algorithm. Mathematically, it is represented by specificity in a percentage by Tn upon Tn plus Fp, and Tn is true negative, Fp is false positive. And accuracy is the proportion of the correctly detected seizures and non-seizures by the algorithm, and mathematically it is represented by Tp plus Tn upon Tp plus Tn plus Fp plus Fn into 100. So in that way, these performance measures have been actually computed, and this table shows the results for sensitivity, specificity, and accuracy of the IMFs with different kernels of the LSSM classifier for classification between non-seizure, that is ZO and F subsets, and seizure as Eeg signals. And here you can see the kernel functions, polynomial, RBF, Mexican head, and Mollet. These kernel functions are studied, and these kernel parameters, L equal to 5, sigma equal to 0.4, A equals to 1, A equal to 0.6, omega G equal to 0.75. They have been obtained based on the trial and error method. And the statistical parameter, that sensitivity, specificity, accuracy, that you can see in the table, and first for IMF1, IMF2, IMF3, IMF4, this is a minimum and maximum value of these performance measures. And in case of Mollet, that you can see the second IMF that provides actually the classification accuracy that is better in terms of like this is for this sensitivity, specificity, and accuracy. These performance measures for Mollet wavelet kernel function out of other methods, this Mollet wavelet kernel function has performed better. That is clear from the classification performance parameters. And there is another actually classification performance measures, that is area under ROC curve, receiver operating characteristics. And receiver operating characteristics is the plot between sensitivity versus 1 minus specificity. So here actually we plot this and then we determine the area under this ROC curve and receiver operating characteristics. And here you can see we have determined the area for all kernel functions. And this Morlet-Wavelet kernel function that provides area under curve equals to 1. So that actually it is very interesting. That is so this is the best performance. So this in this case also Morlet-Wavelet kernel function is giving better performance. So this means actually like this is also validated with the ROC area that this Morlet-Wavelet kernel is giving good performance. And after that, this is actually this is the feature space for testing set of the LSSM classifier with Morlet-Wavelet kernel function that had provided better performance for the second IMF of Eeg Signal. And it is very interesting actually tool that can be used for the computer-aided medical diagnosis system. So like in rural areas, we have shortage of doctors, and urban areas actually we have sometimes we have less doctors and patients are many. And such kind of tools can help you to detect actually epileptic seizure. So like in villages, you can record the Eeg signals, and based on the Eeg signal, you can decompose it by using EMD method and determine the second IMF, then compute bandwidth due to AM modulation, bandwidth due to FM part, and then you map here. So if these features, when you map here, it is coming in this region, then we can say that this person has seizure, otherwise person has no seizure. So in that way, automated diagnosis can be done, automated detection can be carried out based on this tool itself. So like machine learning based classifier that actually even without having doctor, and this machine itself can become a doctor, and that can give you the decision, that can give you the that can be used a decision making system which can tell you you are suffering from epilepsy, and then you can go to urban area and or go to hospital for the further treatment. So such kind of systems are very useful. They are based on the machine learning techniques. And there are various methods in the literature for classification of seizure and non-seizure Eeg signals. And like Tajlas 2007, they use time frequency analysis and artificial neural network. They got 97.73% classification accuracy. Oka 2008 got approximate entropy and discrete wavelet transform together with genetic algorithm got 96.15% classification accuracy. Liang and others 2010 they use time frequency and approximate entropy analysis, linear or nonlinear classifier. They got 97.82 to 98.51% classification accuracy. Ling and others in 2011 they use multi-wavelet transform and approximate entropy features with multi-layer perceptron neural network, and they got 98.27% classification accuracy. And proposed method, which is based on the empirical mode decomposition and bandwidth features, and together with least square support vector machine classifier, it provides 99.5 to 100% classification accuracy. So that our actually method provides better classification performance as compared to the other existing methods in the literature, which are studied in the same database. After that, there is actually we want to detect this epilepsy at any point of time. So now how to do? So that is actually done with the help of instantaneous area. So detection of epileptic seizure based on the visual inspection of Eeg is very time consuming, and especially for long data recording. And suppose somebody driving a car and he or she may have an epilepsy attack. And such methods actually can detect attack in advance, and then required epilepsy drug can be taken. So this such kind of signal processing machine learning based method gives you an automated framework, and where nicely you can actually have alarm or warning that you have to stop your car and take the drugs or take the medicines. And then once you take medicines, then your attack will be bypassed, and then you can start driving the car. So any other activities if you are doing that can be stopped, and in that way such methods are very useful to detect the epileptic seizures in advance. So for this purpose actually there are two types of epilepsy. One is generalized epilepsy and second one is focal epilepsy. Generalized epilepsy, it can be from anywhere in the brain, and this focal epilepsy that is actually come out with a specific region of the brain, and that is actually in 80% cases this focal epilepsy that is actually drug resistance epilepsy. So like medicines doesn't work and you have to go for surgery. And then when you do surgery, then you need to identify the region of the brain from which focal epilepsy is originated. So the signal processing and machine learning techniques play an important role to identify that region automatically so that required surgery can be done in order to remove that area which is associated with the focal epilepsy. And for this, actually, when you go for the surgery kind of thing, then we need very good signals and quality of the signal should be better. It should have high signal to noise ratio. So for that, we actually go for invasive EEG recording. So generalized seizure, surface electrode, there's non-invasive EEG recording sufficient. But in case of focal epilepsy, we have to record signals from the inside of the brain, that is invasive EEG recording. So in this actually work, the data has been recorded from the 21 patients which are suffering from epilepsy, that is focal epilepsy. And this EEG data has been acquired using digital video EEG system with 128 channels, 256 Hz sampling rate, and 16 base analog to digital converter. And in this study, we have actually 3 intra-source reports of 9 patients with focal epilepsy, and which is originated in the temporal lobe region have been selected. And so in that way, total 90 segments per each channel, 51 of them without seizures, and 39 segments noted as having only one epileptic seizure. So now we have to classify them. We have to identify them. So this is actually a very nice example. You see here, this is the EEG signal, and the middle it has got epilepsy attack, but it is not clear from the recorded signal. So when you decompose this signal in terms of IMFs using this EMT method, then you can see this first IMF, second IMF, third IMF. In the middle part is booster. That is actually corresponding to seizure. And when you determine instantaneous area of these each IMF, then you see this is a signal, and these are often instantaneous area of these IMFs. And here, whatever this beginning and ending point which is shown by the circles, that was actually detected by our method. And references is shown by the dashed line, which are obtained from the neurologist. So you can see our method, proposed method, is able to detect the beginning and ending point of the seizures in the benchmark or in the references which have been provided by the neurologist. So here you can see the seizure is becoming severe here, and it can be detected here. So this much time can be used for the providing the warning on taking the required medicine. So that is actually the motivation, because this you see this parameter is not becoming very high here. It takes time. So seizures they actually initiate, and it takes time to become severe. So that time can be used for diagnosis purpose, for the taking medicine. And where this signal processing machine learning real-time implementation of the algorithm is very, very important. And there is a lot of interest in the literature to develop machine learning for real-time implementation, for quick classification of the data. So for doing this purpose, actually for detection, based on instantaneous area of IMFs, you perform the following decision rules. So the first decision rule requires the computation of threshold of instantaneous area of IMFs of Eeg signals for all channels, and the threshold of the mth IMF is computed by the equation 11. And this is empirically derived. And the second decision rule requires the identification of those seizure activities which are available at least 2 of the 3 instantaneous area of IMFs of each channel. And the third rule requires making an interchannel decision based on the identification of those seizure activities which are available in at least 2 of the 3 channels. So where presence of seizure activities in each channel is decided by the rule 2. So in that way, by doing this, actually out of 3 channels, 2 channels are in the favor of seizure, then we take decision in the favor of seizure. And if it is 2 channels are in the favor of seizure free, then we take decision in the favor of seizure free. And these are the performance measures that proposed method. So in the patients, and these are the segments, considered segment, then true positive, true negative, fast positive, fast negative. Once you have these parameters, then you can determine sensitivity, specificity that already mentioned in the previous slides. And this PPV, that is positive predictive value, NPV negative predictive value, and ERD is error in detection. So these all actually perform measures, they are computed, and the sensory specificity PPV and NPV, these parameters are expected to be high. And you can see in the proposed method, they are high also. Similarly, this ERD is expected to be less, and this is coming out to be less. So this actually, whatever is expected, and our proposed method provides you the performance accordingly. After that, we have compared our method with other existing methods in the literature, like Orozco and others, 2009. They use energy of IMFs of Eeg signals, and they got various parameters that you can see in the table. And Korai and others, 2009, they use energy of Eeg signals. They got the various parameters, performance measures. And our proposed method that is based on the instantaneous area measure of the analytic IMFs of Eeg signal, which provides better performance than other existing methods in the literature. That is actually so this shows the method is performing better than the other existing methods. And after that, actually, we have proposed this time frequency image based features for classification of sleep stages. That is actually a very important part. Sleep. When you sleep, there are various sleep stages, and they are changing with time. They are changing when you sleep. Even you don't know how they are sleeping, they are highly correlated. And this time frequency domain, like case of Fourier transform, this is a bridge between time domain and frequency domain. And this individual time domain and frequency domain, they are not suitable for non-stationary signal analysis like Eeg signal. So we combine them, which gives you time frequency representation, where you can see how these frequencies are changing with time. So they are highly suitable for analysis of Eeg signals. So in this work, there is one such technique is pseudo Wigner-Wheeler distribution method, smooth pseudo Wigner-Wheeler distribution, that is used for the time frequency representation that we will see. So these Eeg signals, they are actually commonly used signals for the classification of sleep stages, and this is multi-class classification problem. Like whatever earlier we have seen, there are two-class classification problem. Here it is multiple class. So according to RNK standard, which has proposed around 1965, this sleep can be represented by 6 stages. So that is like awake, non-rapid eye movement S1, S2, S3, S4, and rapid eye movement. So total 6 sleep stages are there. And this rapid eye movement, that is actually in India we call it Brahma Murta, morning time, that is deep sleeping. And this is actually a very important sleep, important stage of sleep, where actually one see the dreams, one can see the dreams. And these alcoholic people, they cannot see the dreams, because alcoholic people, he or she doesn't go to that stage, REM stage, rapid eye movement stage, that is responsive over the dreams. So they have sleep which is incomplete. So these alcoholic people indirectly they accumulate sleep disorders, and this rapid eye movement stage, that is actually one of the very important stage. And even rural areas, villages, if you have seen the dreams, and if you mention this to your family members and your village neighbors, and then they will ask you what time you have seen the dream. If you say you have seen the dream in the night, then they will not take it seriously. And if you say you have seen the dream in the morning time, do this rapid eye movement time by around 4 to 5 o'clock, then they take it very seriously. They say this may be true. So that is actually one. And also based on the whatever you have seen, according to that, they interpret the dreams. And there are a lot of, even like Ramayana time, this Mandodari, she in the dreams, she observed that Ravan is going to die. And she mentioned this to her husband Ravan, that you are going to die, she has seen in the dream. So all time there was a lot of prediction based on the dreams. And these dreams, like for example, some girls, if they have seen that Bengals in the dream, in villages, rural areas, people used to predict that she is going to get married this year. So that a lot of celebration will be there. They start preparing for that. So there is actually a lot of interpretations. If you see the scorpion in the dreams, then they interpret something else. And if you see the snake in the dream, then interpret something else. So this now there is a lot of actually research going in this direction, where interpretation of the dreams makes sense. So like when you see the different objects, and when you see the different things, then what is the Eeg signal corresponding to that? So people are developing dictionaries, and based on that, one can actually detect what you have seen in the dreams. Even your family members can also see what you have seen in the dreams. That is actually, sometimes you are stressed in the dream, you have seen such type of dream, then you have a lot of fear, and it may lead to heart attack, and that can be detected in advance, and that is actually very good. And such kind of research directions are based on this brain signal processing. So there is another recent method of the sleep staging that is proposed by the American Academy of Sleep Medicine, which combines sleep stages S3 and S4 of RNK standard into single stage, that is known as slow wave sleep. So according to American Academy of Sleep Medicine, we have 5 sleep stages, and according to RNK standard, we have 6 sleep stages. Now we want to classify them in order to understand the sleep disorder, and that is actually a very important part. And this generally doctors, what they do this manual identification of these sleep stages. They take Eeg Signal and they say different stages. But here actually the signal processing and machine learning techniques can play an important role, and they can nicely actually identify these sleep patterns. And if there is any abnormality, there is any missing, or the duration, every stage has a specific interval. So that based on that, the people, doctors, they diagnose for the various sleep disorders. And in the proposed methodology, actually you can see the Eeg signals of sleep stages, 6 sleep stages, and then we obtain time frequency representation using smooth pseudo Vignaville distribution method, and then we obtain the time frequency. Make this time frequency distribution, so the energy as a function of time and frequency. Energy is a positive quantity, so we can convert into image, then make a nice actually time frequency image of Eeg signal can be obtained using this time frequency representation. And actually one of the area these days very popular in machine learning, instead of signals we use image, like convolutional neural network, deep learning methods, where nicely you can use image of the data. And suppose you have one dimensional signal and you have real life signal, how to convert into image. The time frequency distribution can play an important role. It can give you nice image, and you can directly apply this image as an input to CNN for classifying them. So this segmentation of time frequency image is based on the frequency bands of rhythms. So Eeg signal, when you go to doctor, they perform analysis in terms of rhythms. So each rhythm actually represent different frequency band. So this features actually based on the histogram of sub images of the Eeg signals have been computed, and then we provide these features as an input to multi-class least square support vector machine classifier, which will automatically classify this into 6 sleep stages for RNK standard and 5 sleep stages for American Academy of Sleep Medicine. And for this purpose, we have actually taken Eeg dataset, which is publicly available online at PhysioNet website. And this data has been obtained from the 8 males and females whose age vary from 21 to 35 years. And the recording includes horizontal epigeneric seizure Eeg signals, each sample at 100 Hz. And according to RNK standard, this entire sleep actually has been segmented. Data is segmented to 6 stages. And the signals have been recorded from night 12 o'clock to 5 o'clock in the morning. So 12 o'clock to 5 o'clock, this 5 hours time is sufficient to cover the all stages which is required for good sleep. So that is actually 5 hours time can have the 6 sleep stages. So this is now we'll see some results. The smooth pseudo-Vignaville distribution, which is computed by this equation 11, and this time frequency representation looks like this. So this magnitude, this is a positive quantity. So then we convert it into image, and this is the gray image representation of time frequency image using a smooth pseudo-Vignaville distribution of REM sleep state of Eeg signal. And here you can see this according to different frequency bands. So like delta rhythm, theta, alpha, beta, and gamma rhythms, we can segment these gray and binary sub-images into different frequency bands or sub-images, and then we determine the histogram for each sub-image. So this actually this shows the histogram of gray and binary sub-images of time frequency image corresponding to frequency bands of delta rhythm, theta rhythm, alpha rhythm, and beta and gamma rhythms. Then we have proposed set of features based on the histogram of sub-images of the Eeg signal. The maximum count of pixel intensity in the histogram of gray sub-images is defined by the equation 12, and spread in the histogram of gray sub-images which is defined by the equation 13, and aspect ratio in the histogram of binary sub-images which is defined by the equation 14. So based on these features, actually we can classify them by using machine learning method. So while earlier we have seen that is two-class classification problem, and here it is multi-class classification problem. So here we need multi-class least square support vector machine-based classifier. So the decision function of multi-class least square support vector machine classifier is defined by the equation 15. And here you can see instead of one kernel, here you need multiple kernels. And based on the sign, you can take the decision. And here k x comma xi is the kernel function for the kth class. And that actually, so in this work, we have used the following kernel functions. So equation shows this kth class kernel function for RBF kernel, and sigma k controls the width of that RBF kernel, and Mexican head wavelet kernel function is defined by the equation 70, and then Morlet wavelet kernel function defined by the equation 80. And this table shows the actually results. And there was a question why we need actually segmentation. So what we have done, we have shown like without segmentation and with segmentation, what is the performance. So we observed that when you perform segmentation, and then actually there is huge improvement in the classification performance. So that is sometimes when sometimes more features are required to understand the data, to classify the data, and when you perform segmentation, there you have more number of features. So when without segmentation of time frequency image, here you can see this RBF, Maxwell head Morlet kernel functions. These are the parameters based on trial and error method, and these are the obtained total accuracy. So for example, Morlet case, the obtained accuracy is 79.99%, and with segmentation of time frequency image, you can see this Morlet case, you are getting 92.93% classification accuracy. So that is actually, there is huge improvement in the classification accuracy based on this segmentation of time frequency image. And then this is actually, this is a confusion matrix for the classification accuracy of sleep stage signal for Morlet wavelet kernel with window size of 64 samples, and for the SAVAC, S1, S2, and STS for RAM and accuracies. So these are actually this automated score. So, and then we have compared this method with other existing methods in the literature. For RNK standard, this is Doronskov and others 2007, they use FFT based feature regional Markov model, and they got total accuracy of 61.08%. In Burale and 2010, they use hybrid features and cluster based classifier using principal component analysis, and they got 69.98% classification accuracy. And proposed method, that is time frequency based features and multi-class decision square support vector machine classifier, which gives you 88.47% classification accuracy. So that you can see proposed method is able to provide better classification than other existing methods in the literature. And we have also compared our method with the American Academy Medicine standard, and Seward others 2013, they use energy-based features and Lehman neural classifier. They got 87.20% classification accuracy. And our proposed method, which is based on the time frequency image-based features and multi-class square support vector machine classifier, they provide 92.93% classification accuracy. So in that way, actually, a nice this improvement in the classification can be seen. And the last part of this talk, that is actually focused on human emotion classification. It is very important part these days, and human emotion is one of the actually key part of human. That actually we can have nice happy emotions, we can laugh. Many animals cannot laugh, and there are very emotions, and human can actually present. And that is a very important part. And if you have anxiety, stress, emotion related disorder, and if you go to doctor and they take your Eeg signal, and Eeg signal one of the nice tool to detect the emotions. So Eeg signal contain variable information which are related to the different emotional states, which help us to understand physiology and psychology of the human brain. And generally emotions are measured by the face recognition and speech processing, and both methods can be manipulated, and should do that Eeg signal based actually emotion detection is more reliable method. So also this emotion classification using Eeg signal can help us to develop improved brain computer interface BCI system. That is actually one of the important direction these days, where like physically disabled person cannot say, suppose he is not well and you are doing treatment for him, he doesn't able to tell whether he is feeling well or not. So the Eeg signals can help you and you can record Eeg signals. Based on the Eeg signal, you can determine the emotions. If a person is happy, this means treatment is showing its effect, and he is unhappy, this means he still requires treatment. So in that way, this is actually very useful technique, that is brain-computer interfacing, where you can actually you can understand the requirement of people. They are disabled. They cannot interact with the real world with the help of machines, with the help of such kind of systems. You can interact with them. So this BCI system can be used for assisting the physically disabled and impaired people to interact with the real world. And this is the proposed methodology where we have experimental setup, pre-processing, then multi-wavelet transform. And then we determine, based on this transform, we have subband signals. Then we determine Euclidean distance-based features from three-dimensional phase space reconstruction. And once you have these features, then you give them as input to multi-class least-square support vector machine classifier, which will classify automatically happy, neutral, sadness, and fear emotions. For this experimental purpose, we have actually collected EEG database from 8 healthy subjects, 4 males and 4 females, whose age vary from 20 to 35 years during audio video stimulus. And these subjects were undergraduate students or employees from IIT Indore. And 16-channel EEG module Biopec system is compliance to the international 10-20 system was used for the recording of EEG signals. And the sampling rate was 1000 Hz for the EEG signals with bipolar montage for this study. And this study has examined 4 emotional states: happy, neutral, sadness, and fear. And in this experiment, 3 audio video stimulus with 5 trials of each emotion from 8 subjects with F3F4 channel of EEG signals have been used. So we have total 480 EEG signals, and each signal has 2 second duration. So here you can see these are the electrode locations for recording such signals in the electrode cap. And this location of these emotions can be seen in arousal and balance diagram. So all emotions, whatever we have considered, they are representing different parts of this arousal and balance diagram. So this is the complete methodology. So here you can see the subject is watching video, and from this video, these emotions are introduced, and then they can be recorded using EEG signals in the computer, and then we can perform the pre-processing, because the data can have noise artifacts that can be removed, and then you apply the signal decomposition. Then we obtain the features from these components, and then we apply multi-class G-square support vector machine based method for classification of these emotions. So this multi-wavelet actually transform is the extension of the idea of scalar wavelet transform, where we need multiple scaling functions and associated multiple wavelets instead of singular one. And this multi-wavelet offers many advantages, like simultaneously exhibit orthogonality, short support, symmetry, and second order approximation. And 3 commonly used multi-wavelets are employed in our work, like GHM, CL, and SL4. And after that, once you have subbands from the multi-wavelet decomposition, then we have to actually understand the dynamics with these subbands, which is linked with these subbands. So there is very important concept, that is phase space in reconstruction. So that actually takes you high dimensional space, where you can see the variation in the representation corresponding to different emotions. So in order to obtain the nonlinear dynamics of the subsignals, obtain the multi-wavelet decomposition, we have used phase space reconstruction. And the phase space reconstruction mathematically can be expressed by this expression. And this is one example of the third level subsignals obtained by CL multi-wavelet. So in this we have 4 subsignals, subband signals, and you can see phase space reconstruction plot of these 4 subband signals. Now there is a variability in this plot, and how to quantify this variability. So that we have proposed some features. So mean of equivalent distance and standard deviation of equivalent distance. These features can be computed from this 3-dimensional phase space reconstruction plot. And based on this equivalent distance is 1-dimensional. So this is just one single value of these features. And once you have this, then nicely you can give these features as input to support vector machine based classifier. And then these features actually summarize the information which is related to the emotions available in the phase space reconstruction plot. And then features have been used as an input to multi-class square support vector machine classifier with RVF kernel and radial basis function kernel, Mexican head and Morley wavelet kernel functions. And this actually, this table shows the classification accuracy in terms of percentage with different kernels of the multi-class least-square support vector machine classifier for emotion classification from Eeg signals using different multi-wavelets. So you GHM, SA4CL, and you can see different kernel functions. And these are the trial and error based values. And for the different emotions, happy, neutral, sad, fear, you can see the obtained classification accuracy. And when you see the total accuracy, then the CL multi-wavelet with Morlet wavelet kernel function provides 91.04% classification accuracy. And this is the confusion matrix of Morlet wavelet kernel function of the multi-class square support vector machine classifier for classification of emotions, Eeg signal with CL multi-wavelets. And then we have compared our method with other existing methods in the literature. So like linear 2010, they use music of 30-second 24 channel Eeg signal together with short time Fourier transform method. And the KNN and this K nearest neighborhood linear discriminant analysis, they got 82.29% classification accuracy for the same four classes of Eeg signals. And Wenger and others 2010, they use video of 4 seconds with 62 channels, they minimum redundancy, maximum relevance. And together with support vector machine classifier, they got 66.5% classification accuracy for the four classes. And proposed method based on the audio video of 2 seconds with the one channel, it use multi-wavelet transform, and together with multi-class square support vector machine classifier, it provides 91.04% classification accuracy for the same four classes that we have studied. So this is the conclusion of this entire talk. This area which we have measured from the trace of analytic IMFs, which have circular form in the complex plane, can be used as a feature in order to discriminate normal and seizure Eeg signals. And bandwidth parameters, bandwidth due to amplitude modulation, bandwidth due to frequency modulation of the IMFs of Eeg signals can be used as a feature in order to classify seizure and non-seizure Eeg signals. And the classification results and values of statistical parameters indicate that the Morlet wavelet kernel function of LSSBM classifier can provide higher classification accuracy in classification of seizure and non-seizure Eeg signals. And we have proposed a patient-specific system for detection of epileptic seizures using Eeg signals. The instantaneous area which is obtained by using moving window of a smaller size of analytic IMFs can provide good detection performance for rule-based detection of epileptic seizures from Eeg signals. In time frequency image-based representation makes possible to compute histogram-based features of each subimage of Eeg signals corresponding to frequency bands of Eeg rhythms. And the histogram-based features are effective for automated sleep state classification from Eeg signals. And the classification results have shown that Morlet wavelet kernel function of multi-class square support vector machine classifier provided 92.93% accuracy in sleep state classification using Eeg signals. The mean and standard deviation of the equivalent distance based on the three-dimensional phase space reconstruction of subsignals can be useful to measure the emotional changes in the brain. And we have seen the classification results. The Morlet wavelet kernel function of the multi-class square support vector machine classifier with CL multi-wavelet can provide 91.04% classification accuracy for emotion identification using single channel Eeg signals. Thank you very much. If you have any questions, we can discuss.
Sir, if there are questions in your comments, then you can answer those now.
Yeah, just I will see this chat box, no? I think difference between AI and ML already I have answered. Then question is there any difference between N and F subsets? Yeah, there's actually. So this left and right side, the seizure-free interval, the signals have been recorded from the different sides of the brain. So this is the difference. And then question, what is the difference between AI and ML? This is already done. Is there any way to rectify whether the seizure prediction is false negative or not? How false could be false negative? True to be. Yeah, that is what actually, this is a good question. So that is when you go for epileptic seizure, actually, for the treatment or for the disease in the hospital, then they use video EEG signal. So video, like together with EEG recording, they also have accelerometer and some video also. So that symptoms like the movement of the body and the different, sometimes they also use ECG signal, and some other modalities are also used for this prediction of the seizure. Then only they confirm it. EEG is one of the signature for initial stage, and once it is detected, then when you go for the hospital, when they start your treatment, they go for other kind of tests also, other modalities also, which include accelerometer based recordings and video recording, and based on that they actually confirm it. What is the second red line in the slide? Experimental results of seizure identification. This is experimental results, means classification accuracy, specificity, sensitivity for that. Yeah, can I get a copy of the presentation? So I will email this slides to Aryan Rastogi. I have his email address, and he will be shared with you. No questions. Any other questions? If you have, please. Yeah, that is actually, this is one of the important, actually, the question, this BCI, limb, this elbow, your head. Many people, they don't have head, and they develop actually robot arm, and that is controlled by the brain signals. That is BCI. They are actually, you can use artificial arm, but based on the signals, you can control it. That is actually one of the emerging area, that is brain computer interfacing, one of the very useful area, and that is actually a future. A lot of signal processing, machine learning will be useful for that application. Then artificial limbs, artificial elbow, artificial any actually device which can be controlled with the help of brain signals. That is BCI, brain computer interface. So there is saying that whatever you can think, whatever you can imagine, that can be done. And imagination, when you imagine that particular task, that you are moving this left hand, moving right hand, and that according to that imagination, that corresponding EEG signal will be actually generated, and they will control that particular task. So that is known as motor imaginary classification of EEG signals. MI-EEG signal classification, motor imaginary. So you are imagine something, and that will give you the signals for that purpose. Can you also send some references to begin with EEG signals and their analysis using machine learning? Yes, I will do that. Actually, this is one of the very important area, and if you see the abroad, foreign universities, a lot of research work is going on. In India, it is not explored so much, and now many groups are coming. But few years before, when I joined IIT Indore, at that time only very less work was going on in India. But last 10, 12 years, our group has done a lot of work in EEG signal processing. So you go through my publications, and you will find a lot of interesting problems, and I'm sure they will be very useful for you. And our laboratory, we have EEG recording system, ECG recording system, we have phonocardiogram signal recording system. So whenever you are interested, please, you are most welcome to access our laboratory. You can do some work related to that. Any other questions, please? There is any function or package available in any program tool? Yeah, very good. This LSSBM and EMD method, both actually MATLAB codes are publicly available. You can access from the internet and you can use them nicely. Both are publicly available. This EMD method is publicly available. Professor Patrick Flandin, one of the pioneer in time sequence analysis, his website, and others, SBM, LSBM, all are publicly available. Even the SBM is available in MATLAB, one of the function.
Okay, sir, I think we can conclude now. Firstly, I would like to thank you for your time, taking out your time to address us today. I sincerely hope that we all have learned something or the other from today's talk. And secondly, I would like to thank all the participants for tuning in to listen to Sir speak today. This concludes our ML at Talk 3.0. Thank you all for joining.
Okay, thank you very much for this opportunity, and thank you very much